We now proceed with the work-energy theorem. Recall that when a constant horizontal force F displaces a body of mass m through a horizontal distance x, the work that this force does on the body is work which is equal to F times x. From the definition of the Newton's second law, we have force is equal to mass times acceleration. Therefore, equation 1 becomes W is equal to max. The kinematic equation of motion tells us that acceleration is equal to v squared minus v sub 0 squared over 2x. Substituting the two previous equations, we have W which is equal to mass times v squared over v sub 0 squared all over 2x times x. And simplifying, we have W which is equal to 1 half mv squared minus 1 half mv sub 0 squared. But 1 half mv squared is the final kinetic energy K, and 1 half mv sub 0 squared is the initial kinetic energy K sub 0 of the body. Therefore, we can write the equation by W is equal to K minus K sub 0. Work done on a body changes its motion. Equation 5.5 tells us that work done on a body by the net force acting on it is equal to the change in its kinetic energy. This relation is an evidence of work done on a system to its energy. This is called the work-energy theorem. For our first example, a woman pushes a 2 kg cart initially at rest with a force of 350 Newton along a horizontal surface. The cart moves a distance of 4 meters. What is the final speed of the cart, assuming it starts from rest? First, let us determine the amount of work done on the cart. We have W which is equal to Fx. Substituting, we have 350 Newton times 4 meters is equal to 1,400 joules. The work done on the cart is equal to the change in its kinetic energy, which is K is equal to 1 half mv squared. Manipulating equation 5.5 to solve for v squared and substituting the values, we have v is equal to the square root of 2 times w over m, which is equal to the square root of 2 times 1,400 joules over 2 kilograms. And that yields to 37 and 4200 meters per second. For our next example, the kinetic energy of a 5 kilogram object is initially 35 joules. It is then subjected to a constant force so that after traveling 9.5 meters, its speed is doubled. Find its initial speed, its kinetic energy after traveling 9.5 meters, and the constant force acting on it. To solve for its initial speed, we have v sub 0 is equal to the square root of 2k sub 1 over m, which is equal to square root of 2 times 35 joules over 5 kilograms. That yields to 3 and 7400 meters per second. Now, to determine the kinetic energy after traveling 9.5 meters, we have k sub 2 is equal to 1 half mv squared. Then we have 1 half times 5 kilograms times 3 and 7400 meters per second times 2 squared. And that yields to 139.88 joules. And for the constant force acting on it, we have force is equal to k sub 2 minus k sub 1 over x, which is equal to 139.88 joule minus 35 joule all over 9.5 meters, and that yields to 11 and 400 Newton.
When calculating work done by a force, we are not normally worried about the time taken. However, when we wish to look at the capabilities of two machines for playing out a specific errand, we are frequently concerned about how rapidly they can give a specific amount of work. This implies the simple amount work done is not adequate for estimating the performance of a machine. What is often more helpful as an indicator of performance is the rate of which work is done. That is the measure of work that can be done per unit time. This quantity is known as the power. Power is the rate at which work is done. In equation 4, we have P is equal to W all over T equal to FD cosine theta all over T. The SI unit of power, the joule per second or J over S, is called the watt, in honor of James Watt, the Scottish engineer who pioneered the development of the steam engine. The kilowatt or 1 kilowatt is equal to 103 watts, is also commonly used. Watt himself originally introduced the idea of the horsepower or HP as the unit of power.
For our first example, a 1,200 kilogram car can accelerate from 30 meters per second to 50 meters per second in 10 seconds. Neglecting friction and air resistance, what is the mechanical power that the engine of the car provides during this time interval? Let us first determine the amount of work done on the car using equation 5.5, which is W is equal to K minus K sub 0. Substituting, we have 1 half times 1,200 kilograms times 50 meters per second squared minus 1 half times 1,200 kilograms times 30 meters per second squared. And that yields to 9 and 6/10 times 10 raised to 5 joules. Substituting this value into equation 5.6, which is equal to power is equal to W over time, we have 9 and 6/10 times 10 raised to 5 joules over 10 seconds, which is equal to 9 and 6/10 times 10 raised to 4 watts, or 96 kilowatts. For our next example, a lift engine needs to move a completely loaded lift 4 meters between floors in 1.5 seconds. The lift has a mass of 1,850 kilograms. Ignoring friction, compute the weight of the completely loaded lift. What is the upward force in the link or cable when the lift is moving at a constant speed? What is the work done by the engine? And what is the minimum power of the engine to raise the lift at a constant speed? To determine the weight of the complete lifted load, we have weight is equal to mg, which is equal to 1,850 kilograms times 9.8 meters per second squared, which yields to 18,130 Newton. For question B, at a constant speed, forces must be balanced. We have upward force is equal to downward force or weight. Therefore, upward force is equal to 18,130 Newton. To determine the work done by the engine, we have work is equal to F times X, which is 18,130 Newton times 4 meters, which is equal to 72,520 joules. For last question, constant speed means forces are balanced. Now to determine the minimum power of the engine to raise the lifted force at a constant speed, we have power is equal to work over time, which is equal to 72,520 joules over 1.5 seconds. And that yields to 48,436 and 6,700 watts.
Energy, as we have noted, is conserved, making it one of the most significant physical quantities in nature. The law of conservation of energy can be expressed as follows. Total energy is constant in any process. It may change form or be transferred from one system to another, but the total remains the same. In the absence of non-conservative forces, the total mechanical energy of an isolated system, or E sub M, is also conserved. It's simple. E sub M is equal to potential energy U plus kinetic energy K, which is also equal to constant.
For example, students from a physics class visit an amusement park to test their understanding of mechanical energy. They ride a roller coaster that starts from rest at a point A with a height which is equal to 20 meters and moves without friction. Determine its speed at points B, C, D. What constant deceleration must be applied at point D to bring the car to a stop at point E? Point E is 15 meters away from point D. Assume that the mass of the roller coaster car and its passenger is 3,500 kilograms. To solve question A, at a point A, kinetic energy K sub A is equal to 0, which is at rest. Therefore, the total mechanical energy of the roller coaster car and its passenger is mechanical energy at point A is equal to U sub A plus K sub A, which is equal to 3,500 kilograms times 9.8 meters per second squared times 20 meters plus 0, which is equal to 686,000 joules, or 6 and 8600 times 10 raised to 5 joules. At point B, the total mechanical energy of the body is in the form of potential energy as well as kinetic energy. At this point, where h is equal to 5 meters, the potential energy becomes U sub B is equal to 3,500 kilograms times 9.8 meters per second squared times 5 meters, which is equal to 171,500 joules, or approximately 1 and 7,200 times 10 raised to 5 joules. But according to conservation of mechanical energy, E sub m is equal to U plus K is constant. Thus, the mechanical energy at point A is equal to the mechanical energy at point B. Then we have 686,000 joules is equal to 171,500 joules plus K sub B, where K sub B is now equal to 686,000 joules minus 171,500 joules. And simplifying, we have 514,500 joules. And the kinetic energy at point B is 5 and 1500 times 10 raised to 5 joules. We use the value of K sub B to solve for the speed of the roller coaster car and its passenger at point B. Manipulating equation 5.4 and substituting the values, we have V sub B is equal to the square root of 2K sub B over M, which is equal to the square root of 2 times 5 and 1500 times 10 raised to 5 joules, all over 3,500 kilograms, and that yields to 17 and 1500 meters per second. Repeating the same procedure for point C and D, we have at point C, U sub C is equal to 3,500 kilograms times 9.8 meters per second squared times 16 meters, which yields to 548,000 joules, or 5 and 4800 times 10 raised to 5 joules. But according to conservation of mechanical energy, E sub m is equal to U plus K in constant. Thus, the mechanical energy in A is equal to the mechanical energy in C. We have 686,000 joules is equal to 548,000 joules plus K sub C. We have K sub C is equal to 686,000 joules minus 548,000 joules, which yields to 137,200 joules. Simplifying K sub C, we have 1 and 3700 times 10 raised to 5 joules. Using the value of K sub C to solve the speed of the roller coaster car and its passenger at point C, we manipulate the equation 5.4 and substitute the values. V sub C is equal to the square root of 2 K sub C over M, which is equal to the square root of 2 times 1 and 3700 times 10 raised to 5 joules over 3,500 kilograms, which yields to 8 and 8,500 meter per second. For point D, we have U sub D is equal to 3,500 kilograms times 9.8 meters per second squared times 1 meters, which is equal to 343,000 joules, or approximately 3 and 4,300 times 10 raised to 5 joules. But again, according to the conservation of mechanical energy, E sub m is equal to U plus K, which is constant, and thus the mechanical energy in A is equal to the mechanical energy in D. We have 686,000 joules, which is equal to 343,000 joules plus K sub D, where K sub D is now equal to 686,000 joules minus 343,000 joules. Now K sub D is equal to 343,000 joules, or this is 3 and 4,300 times 10 raised to 5 joules. Using the value of K sub D to solve for the speed of the roller coaster car and its passengers at point D, manipulating equation 5.4 and substituting the values, V sub D, which is equal to 2K sub D over M, is now equal to the square root of 2 times 3 and 4,300 times 10 raised to 5 joules, all over 3,500 kilograms, and that yields to 14 meters per second. And for the solution for question B, we use the equation 2.5 to determine the deceleration that will bring the car to a stop. We have acceleration is equal to the final velocity v squared minus the initial velocity v sub 0 squared all over 2x. Substituting, we have 0 squared minus 14 meters per second squared all over 2 times 15 meters, and that yields to negative 6 and 5,300 meter per second squared.
Thank you very much for watching. We hope that you learned. See you on our next topic. Bye!